Modern AI foundation models possess an impressive capacity to reason through complex tasks. Yet, place a robot controlled by these models on a slightly different desk, alter the lighting, or change the background, and it freezes. The current industry standard relies heavily on vision language action models, or VLAs. These massive systems are trained almost exclusively on millions of two-dimensional images to navigate their environment. Relying on two-dimensional images forces these models to memorize pixel-level textures. In these systems, the robot learns what a target object looks like under specific studio lighting, while ignoring the physical volume and shape of that object in three-dimensional space. Introducing a novel shadow, an unseen background pattern, or shifting the camera angle by just 30 degrees causes these systems to fail completely. The model cannot map the new arrangement of pixels to its training data. This chart details the average success rate of various robotic policies. Under in-the-wild conditions, representing unfamiliar objects and environments, the industry-standard OpenVLA model achieves only a 3.75% success rate. The FP3 model achieves an 82.50% success rate under those exact same conditions. Consistent robotic execution in dynamic environments requires abandoning flat, two-dimensional matrices for a modality that natively encodes physical geometry. FP3, or 3D Foundation Policy, is a 1.3 billion parameter language visual motor model engineered specifically to solve this perception gap. Instead of relying on a standard two-dimensional camera feed, this visualization displays a three-dimensional point cloud of a physical workspace from an overhead perspective. This data structure records precise X, Y, and Z coordinates for every visible surface. To capture this spatial data, the hardware utilizes a dual camera system, employing one sensor mounted directly on the robot's wrist and a second camera positioned for a third-person view. This dual-view setup generates a point cloud that maintains coordinate invariance. The spatial measurements between the robotic arm and a target object remain mathematically stable, regardless of where the camera is positioned or how the ambient lighting changes. Processing millions of three-dimensional data points at a massive scale cannot be done efficiently with traditional visual networks. It requires a specialized architecture designed to ingest multiple diverse data streams simultaneously. Translating the environment from arrays of pixels into a persistent three-dimensional coordinate space bridges the gap between digital reasoning and consistent physical execution. Feeding a raw, high-dimensional, three-dimensional point cloud directly into a neural network demands immense computational power, creating a severe bottleneck for real-time robotic control. To resolve this, the system first isolates the immediate workspace by applying a strict bounding box. Any geometric point falling outside a 1-meter radius from the target area is instantly culled from the dataset. The remaining data is then mathematically distilled using farthest point sampling. This technique reduces the cropped cloud to exactly 4,000 essential points while retaining the original color and semantic information of the objects. These 4,000 geometric nodes are routed through a Uni3D vision transformer encoder. This block converts the raw spatial coordinates into standardized digital tokens, generating a mathematical embedding of the physical space. Simultaneously, natural language instructions are processed through a clip text encoder, while the robot's own joint positions, its proprioceptive states, are processed through multi-layer perceptrons. Both of these inputs are structured into tokens identical in shape to the spatial embeddings. Mapping heterogeneous physical, kinematic, and semantic inputs into a strictly unified token space gives the transformer the ability to compute them all simultaneously, treating space, language, and motion as a single continuous mathematical equation. The architecture's transformer encoder receives these streams of unified tokens. It fuses the physical geometry, the language command, and the robot's current kinematics into a single comprehensive latent context vector. On the right side of the architecture sits the action diffusion transformer. This decoder unit ingests raw Gaussian noise blocks and is responsible for computing the exact physical movements required to execute the task. Instead of predicting a single instantaneous motor command, the decoder predicts an entire sequence of future movements, known as an action chunk. Formulating trajectories in chunks prevents the robotic arm from getting trapped in local minima or halting mid-motion. The mechanism linking the encoder's situational awareness to the decoder's physical execution is adaptive layer normalization, or ADALN. During the generation process, ADA-LIN conditions the diffusion transformer at every layer. It systematically strips away the raw Gaussian noise, refining the data block until a precise Cartesian action trajectory is revealed. By actively guiding the denoising phase, ADA-LN guarantees that the final generated action chunk is strictly bound to the true geometric constraints and semantic goals of that exact environment. A 1.3 billion parameter neural network requires a massive, diverse initialization dataset to function. Without it, the structural complexity offers no practical advantage. During the pre-training phase, FP3 is fed 60,000 trajectories across 86 different tasks sourced from the Droid dataset. This phase builds the model's baseline understanding of physical manipulation, object interaction, and gravity. The engineering challenge is adapting this massive base model to execute a highly specific, novel task, like pouring a cup of water, without having to retrain all 1.3 billion parameters from scratch. The system relies on a post-train phase, utilizing low-rank adaptation, or LoRa. This method isolates and updates only a tiny fraction of the network's weights, enabling targeted, parameter-efficient fine-tuning. Mastering a completely new physical action requires only 80 total demonstrations, just 10 per environment. The entire fine-tuning process takes precisely 2 hours on a single commercial GPU. The large-scale pre-training establishes a baseline of physical common sense, while LoRa provides rapid task specialization. This pipeline effectively eliminates the severe data scarcity bottleneck that has historically stalled robotic automation. The true validation of this architecture requires moving the hardware out of the controlled lab setup and deploying it in the wild scenarios featuring unseen objects and entirely new environments. In these conditions, image-based models get confused and attempt to grasp shadows or irrelevant background objects the moment a novel light source or a visual distractor is introduced into the frame. This panel captures FP3 executing tasks with zero-shot generalization. The hardware successfully manipulates unseen objects despite the introduction of completely novel lighting conditions, visual distractors, and unfamiliar background surfaces. Unlike the erratic mood attempts of older baseline policies, the sequence of action chunks generated here yields a smooth, continuous trajectory toward the target. By anchoring its perception in a three-dimensional point cloud, the architecture prioritizes spatial geometry over visual cosmetics. The system bypasses the domain shift failures that consistently compromise image-based controllers. FP3 solves a critical vulnerability in automation by replacing two-dimensional pixel arrays with precise geometric points and processing them through a scaled, unified diffusion transformer. Three-dimensional awareness serves as the mechanical baseline for any autonomous interaction within a physical environment. A machine's ability to execute complex tasks in dynamic environments is permanently bound by its capacity to perceive true spatial depth.